geometric flow.
Yeah. Thank you. Yeah, I would like to thank Professor Park for inviting me to speak here. So yes, I would like to talk about some results on geometric flow. So I would like to talk about prescribed curvature flow. And second, I would like to talk about Yamabe flow. And if I have time, I would also like to talk about curvature flow. But I don't think we have time for this. But anyway. So first, let me begin with a definition. So suppose a G and G naught are just some Riemannian metric. Okay, on a manifold, on a Z infinity manifold, on a manifold M. So then we said that G and G naught, G, so they are conformal, or we say that G is conformal to G naught. Okay, if we can find a function U which is C infinity and U which is positive, okay, such that so G is equal to U G naught. Okay. So and it is easy to check it is equivalent relationship, right? So it's easy to check. There's an equivalent relation. Okay, so and then so we can talk about the equivalent class, right? So we can talk about the equivalent class. Okay, so this is generally called conformal class. Okay, so which consists of all metric G, which is conformal to G naught. Okay. So it's easy to check that two conformal metric preserve angle, right? So they have same angle. So even they have different names. Okay. So with these definitions, I can talk about one very classical theorem. So which is called uniformization theorem. Okay. So there are many different ways to state it, but so that's the way I would state it. So suppose M is a two-dimensional manifold, okay, and it is compact and without boundary. And so if you want, you can assume that it is orientable. So you can just assume by considering the orientable covering. So you can assume that M is orientable. So and suppose G naught is a given metric, is a given Riemannian metric on M. Okay. So uniformization theorem says that we can find G. There exists a metric G, which is conformal to G naught such that the Gaussian curvature is Gaussian curvature. So we denote it by Kg. So this is equals to constant. Okay, so uniformization theorem says that we can always do that. So given any Riemannian metric on this surface M, so we can always find a metric G, okay, in the conformal class, which is conformal to G naught, such that the Gaussian curvature is equals to constant. Okay, so that's one way to define to state it. Okay. So then we can ask a more general question. So we can ask the questions which kind of generalize uniformization theorem. We can ask, so given a smooth function f on M, okay, so we still assume that it is two-dimensional and it is compact, it is without boundary, okay. So given any smooth functions, so can we find, so does there exist G conformal to G naught such that the Gaussian curvature is exactly equals to F, okay, can we do that? So if F is constant, so this reduces to uniformization theorem. Right? So if F is constant, so uniformization theorem says that we can always do that. Okay. So this equivalent to solving this PDE, which is like this U KG naught. Yeah, I don't want to state it, but anyway. So we'll not use it. But so suppose if G is equals to exponents of 2U multiplied G naught, so then the Gaussian curvature of G and G naught satisfy these equations. Okay. So which means we want to solve these differential equations, okay, by putting this being F, okay, so this a partial differential equations of elliptic type, okay, because this is Laplacian. So by the way, so this is Laplacian. Oh yeah,
So,
go ahead. Yeah.
In the uniformization theorem, do you need to suppose something about the sign of the constant, depending on the units of M? Or?
Sure, we need to do that.
Okay.
Yeah, we need to do that.
Okay.
Yeah, but I just assume that it is constant. Some constant.
Okay.
Whether it is positive, negative, or zero.
Okay. So depending on the genus, maybe some constant doesn't work.
Yes, exactly. And that's what I'm going to talk about actually. Thank you. Oh, no. Yeah. So, and this clarifies our things actually. So, and actually we need to assume something, right? So there's necessary conditions. So there's necessary condition for this to be true, right? So because which exactly coming from Gauss-Bonnet theorem. So Gauss-Bonnet theorem tells us the integral of the Gaussian curvature is equals to 2 pi multiply the Euler characteristics, right? So this Euler characteristics. Okay, so which means if you can do it, if you can prescribe your Gaussian curvature to be F, so which means the integral of F over M is equals to 2 pi multiply Euler characteristics, right? So of course, so then this implies F and Euler characteristics should have somewhere, so have same side somewhere. Okay, so there's necessary conditions. So and in particular, if F is constant, so which means F, that constant should have the same sign with the Euler characteristics. So then we can ask, so is that sufficient? So, and it depends on the sign. So there are 3 cases. So if the Euler characteristics is negative, so then we have this theorem, which is by Castan and Warner. So basically they're pioneer actually. They were the first people consider this kind of problem. So Castan and Warner said if F is a non-positive function and F is not identically equal to 0, so that we can do that. So then there exists G, in the conformal class of G naught, such that the Gaussian curvature is exactly equals to F. Okay, so basically that's all what we know about this case. So, and then for the case Euler characteristics equal to 0, so this is solved. So this is solved completely. So this was solved by Castine and Warner. And also solved by Bourdieu. So basically, he obtained some necessary conditions, and then later they proved that it is also sufficient. Okay, but we will not talk about it for the rest of my talk, so I don't want to stay it. So basically, it is solved. So we know the sufficient and necessary conditions. Okay, so and then for the positive Euler characteristics, so of course, which means M is sphere, so which means M is just S2. Okay, so this is so-called a Newton-Burst problem. So and so this was studied by many people, like Alice Chan and Paul Yang, and many people like Moser and many others. So, and in particular, Smoothy, so he is a German mathematician. So he defined something called prescribed curvature flow. So he defined the prescribed curvature flow to attack this problem. I'm going to define it. So, which is in this way, define it. Okay, you try to deform the metric G according to this. Yes. So here K is the Gaussian curvature. Gaussian curvature of GT. Okay. Okay. So actually, you should write this as this: K equals to GT. Okay, but I just understood it. Okay, I just don't write it. Okay, and F is that given function. Okay, so F is the given function, and alpha is a constant. I don't think I have space. So alpha is a constant, only depends on t. Okay, is defined as the following. Okay, so you just want to keep the volume fixed. Okay, that's it. So alpha just help you to keep the volume fixed. Okay, so this is really like the Ricci flow, right? If you see it, right? So we want to deform the metric according to this law, right? So we want to try to make the Gaussian curvature to be F up to some constant. Okay, so and then Smoothy is the one who he want to attack the Newtonsburg problem by using this flow. Okay, so then what I do is the following. So instead of considering prescribed curvature flow for this case, for the case of positive Euler characteristics, I consider this case, negative case. So suppose this is negative, and then the function f, but a little bit weaker than this. So f is strictly negative. So then I consider this, let's call this star. So So this is star. Okay, so then I prove that star exists for all time. Okay, and it converge and converge to some metric. We call it G infinity. Okay, such that so the Gaussian curvature of this this limiting metric exactly has the form that we want. Okay. So here, this is some constant. So this is just some constant. Okay. So which means I use prescribed curvature flow. So to kind of recover this theorem. So, but it's a little bit weaker because I assume that F is strictly negative. But so somehow we always can rescale the metric to take this away. So which means we can always prescribe the Gaussian curvature to be F, if F is elective functions. Okay, so that's the case. So then, so similar result was obtained when M has boundary. So now if we suppose, so M is still two-dimensional manifold. Okay, assume that it is compact. Okay, but this time we assume that it has smooth boundary. Okay, which is given by 1M with smooth boundary. So again, we have uniformization theorem actually. So again, we have uniformization theorem, which is due to Peterson arc and some other people. I couldn't remember their name, and others. Yeah. So, but this time you have two ways to uniformize the metric. So, first you can have there exists G conformal to G naught, such that Kg is equals to constant. And the geodesic curvature that equals constant, sorry. Okay, geodesic curvature equals to 0, which means the boundary is like the geodesic. Okay, so for example, this we have the case of half sphere, like this. Okay. So the second case is again there exists a conformal metric. Okay, such that, but this time we require the Gaussian curvature is 0, okay, in the interior, but the geodesic curvature is equals to constant. Okay, so examples is like disk, the flat, the disk. Okay, so the flat disk, with the standard metric, just the flat metric. Okay, so so again we can ask the similar question. So corresponding to this one, given. So here's the question. So given H, which is C infinity on the boundary. So does there exist G conformal to G naught such that Gaussian curvature is 0 in the interior, but the geodesic curvature is exactly equals to H. Okay, so can we do that? Okay, and so same result was obtained. So yeah, I just say it without stating it. So using kind of similar prescribed curvature flow, I prove that so if H is negative, And for the negative Euler characteristics case, so I can do that. So. Okay, so people want to generalize the uniformization theorem to higher dimensions. So there are many possible ways to generalize it to higher dimension. And Yamabe problem is one way. So Yamabe problem is one way to generalize the uniformization theorem. So now we suppose M is a n-dimensional manifold. So compact n is at least 3. Okay, so we consider higher dimensional case. And again without boundary. Okay, again G naught is a Riemannian metric on M. So Yamabe problem is to ask, so whether there exists a metric conformal to G naught such that, so this time I ask for scalar curvature. Scalar curvature, we denote it by RG, equals to constant. So Yamabe problem is to ask, does there exist some metric conformal to G naught such that the scalar curvature is constant? So and this is equivalent to solving again a elliptic PDE. So I want to state it. So if if G is equals to U to the power of 4 n minus 2. Okay. So of course U should be positive as we said. So then we have the following. So 4 n minus 1. Okay, so this is equivalent to solve this PDE of elliptic type. Again, this is Laplacian, right? So this is Laplacian of G naught. Okay, so which is a elliptic type PDE, right? So elliptic type PDE. Okay, so which means we want to find the solution U, okay, such that this is constant, right? We want to put this to be constant. Okay.
How come you choose the number of 4 over n minus 2?
Oh, that's a good question, because if I choose the index to be this, I can write these equations in this nice form. Okay. For other indexes, kind of messy, you know. So if we write this to be 4 divided by n minus 2, we can really see that this is a quasi-elliptic differential equations. Okay, for other index, you can try. Actually, it's messy, you know. It's kind of messy, you know. This is like linear terms plus some index term, you know. So if you use other index, like what we have used in the past, like exponents of something, then.
If we use your order index, don't we have the Laplacian? We have an order 3.
Yeah, that's right. Yeah, that's right.
Okay.
Yeah. Okay. And is it nice? Isn't it? So, right. Yes, so this is really similar to uniformization theorem. So depends on the Yamabe constant. Okay, so this is Yamabe constant. Okay, which is defined as the following, which is taken as the infimum among all the metric in the conformal class. Okay, such that we take the integral of the scalar curvature. Okay, it's kind of long. So subject to the condition that the volume is 1. So which means you just integrate this. So this is equals to 1. Okay. So this is called Yamabe constant. So for the two-dimensional case, this is nothing but Euler characteristics. Right? So it depends on the sign. So if this is non-positive, so Yamabe problem was solved by Schrödinger. So Schrödinger. Okay. So the difficult case is the positive case. So when this is positive, so first O'Brien, so he solved the case. When n is at least 6. And M is not locally conformally flat. Okay, so what this means is it means just locally it looks like the plane. Okay, just means locally conformal to our n. Okay, or sphere, doesn't really matter. So he solved this case, and we shown. So he solved the remaining case. So he solved the case, namely m between 3 to 5. Or M is locally conformally flat, or M is locally conformally flat. By using positive mass theorem, positive mass theorem. Okay, so which is kind of very deep results. Okay, and later, so Barral, so he obtained the same result of Richern. So obtained, or how do I say it? Obtained the same result as Richern. Okay, without using positive mass theorem, he used something called critical point at infinity. So which is something I don't really understand, but it's like counting the Morse index. So maybe some of you are expert, but I have no idea what it is. Anyway, so and then so that's Yamabe problem. So it was solved, but later Hamilton. So Richard Hamilton. So he wanted to use the flow technique to attack this problem. So they want to consider Yamabe flow. So in order to solve the Yamabe problem, which is given by this, which is very similar actually. So now we deform the metric, but this time is R minus the mean GT. Okay, so here is the mean. So which is exactly given by the integral divided by the volume. Okay, so if you remember our prescribed curvature flow, so this is like the alpha, right? So this is like the alpha. So anyway, so again, we want to deform the metric such that it becomes the constant, right? So this is again, which is very good PDE because this is a parabolic type. So this is parabolic type, which is good. So Hamilton himself, he proves short time existence. Short time existence. Okay, so he proved that the solution doesn't blow up for finite time. So so that's what he proved. Okay, and he also proved convergence. Actually, he proved convergence, but for the case Yamabe constant is non-positive. Okay, so which is really like the Schrödinger case. Okay, so and for the case of positive Yamabe constant case, so this has been studied by many people, but finally Simon Brando in Stanford, so he proved the long time he proved the convergence. So he proved convergence. Okay, for this case by using positive mass theorem. Okay, which is kind of expected, right? Because here they also use positive mass theorem. So he also used the positive mass theorem to prove the convergence.
So I don't see the connection between the Yamabe flow and the elliptic equations.
With what?
Yamabe
flow with
the elliptic equation. What? So the asymptotic limit of the Yamabe flow will solve the elliptic equation.
It solved the elliptic equations.
Yeah, the equation for U. What is the relation
between this and this?
Yeah, right.
So relation is it's like we want to deform this metric, so that when t goes to infinity, this term equal to 0. Okay.
Yeah.
So if this is equal to 0, which means the scalar curvature equals to constant.
Yeah.
Okay. So which means this solve the Yamabe problem. I already erased it. Which means we can find a metric. Okay. If we call it G infinity, so then this G infinity has constant scalar curvature. Okay. And that, if you write this as G infinity U to the power 4 and minus 2G naught. So and then that U infinity actually we should say. Then G infinity satisfies these equations.
Okay.
Yeah.
And then when you say when Yamabe constant is negative or positive,
right.
it is solved, that means the elliptic equation is solved, right?
Yes, exactly. So yes. So Schrödinger he solved this case, when this is less than 0, non-positive. Sorry. Yeah. Okay. So these two guys solve the case when this is positive. Okay.
Then is it the uniqueness is known?
Yes, it is unique. Yeah. It's kind of easy. Uniqueness is easy. Yeah. Or maybe I should say it in this way: unique in the conformal class. Okay. So maybe there's some other metric which is very different, but unique in the conformal class. Okay. We only talk about these conformal class G naught. Okay. Okay. Because somehow this is the easy case because we can apply maximum principle. Okay. If you look at it from PDE point of view, so we can apply a maximum principle. It's kind of easy. This case, but positive case is more difficult. Okay. Right. Okay, so Yamabe problem can also be considered for the case of CR manifold. So we call it.
What
Sure.
Hamilton did is the short time existence for any case, but the
For any case. I should say.
the constant is negative, then long time global existence plus count.
Right. That's true. Yeah, maybe it's kind of misleading. He proved this for all cases, and then he proved this for the case of non-positive Yamabe constant case. Okay, and right. Yeah, thank you for clarifying. So he proved this too. Is it? Okay. Okay. Any other questions? No. Okay. So, right. So we can also consider CR Yamabe problem. Okay. So first assume M is a strictly. It's kind of long, the definition. Pseudo-convex compact CR manifold of real dimension 2n+1. Okay. So, well, what this means. So let me tell you what this means. So CR manifold means means the following. So means there exists a T10 tangent subbundle of the complexified tangent bundle, which satisfy these three properties. So first, the complex dimension is equals to n. Okay, and then if you intersect with the conjugate, it is equal to 0. So which is like maximal, you see? So which is like maximal. So T10 intersect with conjugate is 0, but the dimension is n. So which is like maximal. So and then it is integrable, in the sense that if you take the Lie brackets, it's still inside the T10 tangent subbundle. Okay, so that explains ZR manifold. Okay, so what does it mean? Strictly pseudo-convex. So strictly pseudo-convex means strictly pseudo-convex means, I didn't say it here. So I should add one more definition. So with contact form. So with contact form theta. So sorry for adding this definition. But this is contact one form, I should say. Contact one form. So then we can define the two form. Okay, the theta, and then taking square root of -1. So this is called Levy form, actually, Levy form. Just some name, okay? Doesn't really matter. You just consider it as a one form, okay? So this is positive definite when you restrict it on T10 cos T10 bar. Okay. So in order to explain it, so let me give you a very easy example. So M is given by the odd-dimensional sphere, and you can consider it in a complex plane, in a complex base. Sorry. So and then this is the contact form, which is given by this J n plus 1. Minus okay, so that's the contact form. So, and you can really check it satisfies all these properties. Okay, so it is a ZR manifold, just a normal T10 subbundle. Okay, it satisfies this. It is integrable, and if you take the differential, the two form, so and then taking the square root of -1, and you can find it even explicitly. So this is also positive definite. Okay, so it is a one of the examples of strictly pseudo-convex compact CR manifold. Okay, and so on CR manifold, one can define a notion of scalar curvature. People call it Webster curvature, or some Webster curvature. So here's students of Chen, or some people call it pseudo-Hermitian scalar curvature. Okay, for this contact form, theta.
The Webster seed Webster? Is the Webster seed Webster?
Yes, yeah. Yeah. So we denote by R theta. Okay, but I don't want to define it, but we can always do it. We can always define the pseudo-Hermitian scalar curvature for this kind of manifold, strictly pseudo-convex compact CR manifold. And for these examples, so for the examples I give you, so this is constantly equals to this. Okay, for these examples I give you.
What is T10 for that example?
Which one?
T10?
Oh, T10?
Yeah.
You just Z1, right? No. You just C1 to Cn, right? Isn't it? C1. Oh, no. This one, right? You're asking this example? So, I see. So this one.
What is T10?
Yeah, so T10. So I can describe it by using the basis, right? So this is equals to. Yeah, that's a good question, but plus some terms minus something like this. Ci, sorry. I and then I from 1 to n. Okay, so but does anyone know this? I'm not sure. Yeah, but it is the linear combination of that. So they're spanned by this. Okay. So
That is constant, right? Equal to the.
no, it's not a constant. It's a function in z. Yeah, if I look at the book, I can tell you, but it's hard. I didn't put it down, but it's like it's a function in z. But anyway, so yeah, maybe I need to speed up a little bit. So anyway, so I have everything here, right? So what CR Yamabe problem is? So you can fill in the details actually. So I have everything here, right? So which is to for M is a strictly pseudo-convex compact ZR manifold, and then theta naught is a given contact form. So yeah, just like you just mimic, right? Mimic Yamabe problem. So that is to find a theta which is conformal, right? Conformal to theta naught, such that the Webster curvature is equals to constant. Okay, so that's Yamabe problem. So, and again, it can be stated as a problem of PDE. So, if theta equals to U2 over N theta naught, so then we know that the Webster curvature satisfies this. I couldn't remember. 2 plus 2n. Yes.
By the way, what
Yes.
does CR mean?
Huh?
In the name, what does CR mean?
Oh, CR means Cauchy-Riemann. Yeah, Cauchy-Riemann. Yeah, Cauchy-Riemann manifold. Yes, yes. Yeah. Right. So it satisfies this theta naught U plus theta naught U equals to theta U 1 plus 2 over N. Okay. So, but here, so which means, you know, to solve CR Yamabe problem is to solve this by putting this to be constant. Okay. So, but here, so here comes the problem. So this is sub-Laplacian of theta naught. Okay. So, and these make these equations not elliptic. So this is only sub-elliptic. So is a sub-elliptic, which means it degenerates in certain direction. Okay, so from PDE point of view, this is much more difficult because of these terms here. But it still is solved. So by two group of people. So first it's solved by Jerrison and John Lee. So they solved the case when n equals to when n at least 2, and when m is not this is like locally conformally flat, but CR equivalent, we call it CR equivalent to S2m plus 1. Okay, so this is like the locally conformally flat case. Okay, so and then if you compare this with Yamabe problem, so this is like the case of Schrödinger and O'Brien, if you look at it. So which means the remaining case, you know, people expect to solve it by positive mass theorem, you know, the case of Richard. But unfortunately, we don't have CR Yamabe problem. But still, people solve it. So there are two guys. So I have no idea how to pronounce their name. So they solve the remaining case, which means when n is equals to 1, and also or m is, you know, CR equivalent to S2m plus 1. Okay, but they were able to solve this case without using positive mass theorem. So they solve it by using the Barrow's trick, by using critical point at infinity. So by critical point at infinity. Okay. So then, yeah, you can kind of expect what I'm going to talk about, right? So we solve Yamabe problem, and then we use Yamabe flow to solve it, right? We consider CR Yamabe problem, then we can use flow technique to solve it. So, which is kind of similar. So you just define this to be 2 theta. So this time it's theta t minus mean. Okay, you deform the contact form. Okay. So, but again, so this is much more difficult from PDE point of view because this is not parabolic anymore. So it is only weakly parabolic. It is only weakly parabolic. So it is much more difficult from PDE point of view. So Yamabe flow is parabolic type, but this is not. Okay, so but still, so Chang and Chung, so they prove short time existence. They prove short time existence. And then, so there's other Chang. Yeah, Chang. So he proved convergence. So he proved convergence for the case. So there's like the negative Yamabe constant case. So we call it theta naught. Okay, negative case. So, and what I did is, I proved the long time existence. So it exists. So for this case, so this exists. So exists for all time. So let's call this star. So star exists for all time. Okay, so but still, you can ask about convergence. So convergence, if you look at Yamabe flow, so we prove convergence by positive mass theorem, right? Remember Simon Brandel, he proved the positive mass theorem. But I said here, right, we don't have CR Yamabe, we don't have CR positive mass theorem. So I'm not able to prove the general convergence, but I consider this case. So our examples over there. So I'm able to prove this case. So if theta, so converge to theta naught, theta S2m plus 1. So under star. Okay. So which means, so remember this has constant Webster curvature, right? So I'm able to prove that. So for this particular case, okay. So but generally, I have no idea how to prove it without CR Yamabe problem. Yeah, maybe I'm thinking about maybe we can prove it by critical point at infinity. So, but as I said, I have no idea what it is. Anyway, so I think I stop here.
So there is some question.